So this is Jeff Hamrick at Rhodes College, and I'm going to spend a few minutes talking about using Fathom to fit a probability density function over a collection of data that you have put into Fathom and are displaying as a histogram. So I've got two different data sets here that I've imported into Fathom. The first data set is the data set that we've been using in class recently, namely random draws from a chi-square distribution with 3 degrees of freedom. Recall that we start off by creating a dot plot of these data, and Fathom is not particularly excited about drawing a probability density function over these dots, but it will do so if we convert the dot plot to a histogram. Now, in order to plot, for example, a probability density function over these data, we actually have to normalize the histogram. Density functions, if you'll recall, have an area underneath them equal to 1, and clearly the area underneath these rectangles does not add up to 1. I can tell that pretty easily because the width of this first rectangle is 1, but the height is roughly 1,000, so that's way greater than 1. So to normalize this histogram, what we need to do is we need to right-click on it and change the scale from frequency to density. The shape doesn't change very much when we do that, but now when we add up the area underneath these rectangles, it adds up to 1. So this histogram is now ready to have a probability density function imposed over it. To do that, right-click and choose to plot a function, okay? And you will pick out the command that you want if you can't remember it. I rarely can remember it. From this section right here called functions, you want a type of function called a distribution. We just said that these are random draws from a chi-square distribution, so choose this particular option right here. We want a chi-square density. So I'm going to click that twice to bring up the function. There are, right down here in the documentation, 4 potential arguments for chi-square density. And we see from this example that we only need 2 arguments at this moment. So I'm going to use this argument x to inform Fathom that x is a dummy variable along which the function should be plotted along the x-axis. And the second argument here is the number of degrees of freedom. So we know from class that that was 3 degrees of freedom. We press OK, and there this function fits the histogram relatively well. Perhaps not perfectly, but relatively well. So what we have here are returns for the S&P 500, the Standard & Poor's 500 index for roughly the past decade. And this data is sort of Gaussian, though maybe it's not terribly close to being normally distributed. Once again, I'm going to change the dot plot to a histogram, and then I'm going to change this histogram over to a density by rescaling it. Okay, this isn't a really great histogram. There's only like 1, 2, 3, 4, 5, 6, 7, 8, roughly 10 bins. I want more bins. So to fix that problem, I'm going to double left click on this histogram and change the bin width to something like 0.33. All right. When I do that, I get a sort of much more fine histogram. And I think if I right-click on this and rescale graph axes, I can sort of shift things around so the picture looks a little bit nicer. And now I want to fit a normal density curve to these data, but I don't know the mean and the standard deviation of these data. Obviously, I'll get that by creating a summary table, dropping the data into it, and then converting the summary table to a basic statistics plot. Okay, so this has this particular mean and this particular standard deviation. So going back to my histogram, I'm going to right-click, plot a function. I don't want a chi-square density anymore. Now I want a normal density, and there are going to be 3 arguments that are relevant for the normal density. The dummy variable, denoting the variable associated with the x-axis, is x again. The mean is 0.0147362, and the standard deviation is 1.37016. So I press OK, and that's not a fantastic fit to the data. It sort of suggests that stock return data is not really approximately normally distributed. It's deviating quite a bit from that normality assumption, but nonetheless it's not a terrible fit to the data. Many of our randomization distributions will be well fitted by a normal density function.